Hey, welcome back. Today I am going to teach you how to simplify radicals, how you can multiply them together, and then also how you can rationalize the denominator, an easy denominator for today. And then tomorrow we'll do a little bit harder denominator. But what I want to just first talk about is kind of the properties of radicals and kind of what exactly that they are. So a radical is another name for a square root. So the radical sign is what makes that, or square root sign, they're kind of referring to the same thing. And there are two properties that we're going to need today to understand how to simplify a radical down. And this is really useful for geometry, and then also when you get to algebra 2 and you start doing trig, like sine, cosine, and tangent of triangles, you'll need to know these properties of square roots. So the two properties that I'm going to focus on today are going to be the product property. Product means multiply. And the quotient product, which simply means a fraction. So a fraction that has radicals in it. Now these are the two properties. The first property, which is your multiplying property, is that if you have two numbers being multiplied inside the radical sign, what you can do is separate them into their own individual radical signs. And this would work for positive numbers, which is why it says your number A and your number B would be greater than or equal to 0. And the reason why we can't do negatives is because if you type in the square root of a negative, like on your calculator, it will say domain error because they don't exist. There's no answer for that. So if I had an example of an A and a B, A, the first number being 4, and B, the second number being 100, it is true for me to say and separate the two radicals that the answer is the same as the square root of 4 times the square root of 100. Now this is really useful for simplifying square roots because hopefully you know without a calculator what the square root of 4 is, and it's going to be the number 2. Just a whole 2, no more square root anymore. And the square root of 100 is the number 10, which means that this answer that we started with, 4 times 100, is the same as 20. Now the quotient or fraction property is really similar. So see how we had these two numbers being multiplied inside of the radical? Well, now we just have a fraction happening inside of the radical because we're using fractions. So it is true to say that you can separate your two numbers, your A and your B, into a radical for the top and a radical for the bottom. So the numerator gets its own radical sign and the denominator gets its own radical sign. So this property says that if we were to take the radical of the fraction 9 over 25, it would be the same as the square root of 9 divided by separately the square root of 25. And hopefully you know your square roots, some of the easy ones, the square root of 9 and the square root of 25. The square root of 9 is the number 3, and the square root of 25 is the number 5. So this fraction, 9 divided by 25, and then if you take the radical, will be the same as the fraction 3 divided by 5. Now these two properties are what we're going to need to know to kind of start today, but I also want to talk about just like parts of the radical. So if you feel like, whoa, you're starting off too fast, I'm going to kind of back up a little bit now. So let's just talk about the words that I'm using. The number or expression that is underneath of the radical sign, the radical symbol is your square root symbol. But the thing inside of that is called a radicand. So if you hear me talking about the radicand, that's the number or expression inside of your square root symbol. Numbers whose square roots are integers, an integer means a whole number, or quotients of integers, meaning a fraction of whole numbers, these are called perfect squares. And if you look at these numbers that I used before, the number 4, the number 100, the number 9, the number 25, all 4 of those numbers are perfect squares. And I'm going to go ahead and make a list for you. And I would highly recommend that you have this list kind of out and handy while you're working on the radicals, as this is going to help you simplify more easily. The perfect square list, I usually just go up to 10, but it might be helpful even if you went up to 15. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. These are all perfect squares. 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, and 10 squared is 100. If you can keep going a little bit further, that might be helpful as we go later on. 11 squared is 121, 12 squared is 144, 13 squared is 169, 14 squared is 196, and 15 squared is 225. And these go on as, high as you square your numbers. Now, the simplest form of a radical, I'm going to explain through here. An expression is in simplest form if these three things are met, these three characteristics. And we would have a simplest form of a radical, so if you simplify it down as much as possible, if this list of numbers cannot be used to broken down your radicand. So if your radicand is divisible by one of these numbers, then this is not in simplest form. Now, if you look at this list of numbers, is 12 divisible by any of these numbers? Well, yeah, it is. 12 is divisible by the perfect square of 4. And so this is not in the most simple form because one of these numbers is a factor of 12. And these are the numbers we have to use as factors. So as I'm looking at the number 12, can I split up 12 into, using this property, one of the perfect square numbers times another number b? So I want to show you like this. So if I'm thinking about that AB product property, I could say that the square root of 12, and using this list, would be the same as 4. I'm using 4 because 4 is in this list, 4 times the number 3. Now, the product property said that I can split up these two numbers into their own radicals. So the square root of 4 times the square root of 3. And now, hopefully you know the square roots of perfect squares. Well, the square root of 1 is, if you need your calculator, go ahead and pull it out, 1. The square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4, and so on. So my most simple form would be to take this part that came from this perfect square list and reduce it down. The square root of 4 is 2, and what gets left behind is that radical 3, because 3 is not in this list. That 3 cannot be simplified. So what we're going to do is go from this to this in most simple form. Now, number 2, what makes most simple form would be if your fraction does not have one of these numbers in the radicand that you can divide out. And I notice here there's a 25, and 25 is a perfect square. So I'm going to use this quotient property to simplify the part of my radical that is able to be reduced because it's a perfect square. So I'm going to use the the quotient property up here because we have a fraction, and split this up into the square root of 5 over the square root of 25. Now, I know what the square root of 25 is. If I use this method that I was kind of writing here, I know that this piece, the square root of 25, is really a whole 5, no more square root. And then the top, the square root of 5, because 5 is not in this list and 5 is not divisible by 4. I mean, 5 is divisible by 1, but 1's not really going to simplify it down for me. But this is the most simplified version of the fraction that we started with. And then the last one, number 3 here, it says no radical can appear in the denominator. So if you have any denominators with radicals, the process of fixing that is called rationalize. So using the same property that I kind of had before. Now notice my 1 does not have a square root, so I'm going to leave that 1 alone. But the square root of 16 I need to simplify, and the square root of 16 is the number 4. And this is the most simplified version of what we started with. Now, if you go ahead and turn your page, I'm going to go through just kind of some simple examples, and just starting with simplifying a radical. And so what I want you to look at here at the top is it says, simplifying the expression, remember, factor the radicand, and remove perfect squares. Think to yourself, are there any perfect square factors inside of your square root? And if there are, then we're going to simplify those out. And then rewrite your answer of that simplified perfect square, and then if there's a radical left over. So my first example here for you is the square root of 160. The highest perfect square from that list that we made over here on the first page. Are any of these numbers from my perfect square list a factor of 160? Yeah. The number 16 goes into 160. And so what I'm going to do by the product property is split this up into a 16 times 10. Now there are other factors of 160, but the most important piece is that you pull out a perfect square. That's what our goal is. And then you simplify your square root of 16 separate from the square root of 10, and then you simplify the square root of 16 as a whole 4. And this 4 square roots of 10 is called the most simplified version of the square root of 160. The decimals for these, if you were to put them on your calculator, are identical, but this is called the most simplified version because you have taken out the perfect square part that can be simplified. So here are a couple more examples for you. The square root of 28, the goal is to use our perfect square list that we made on this other page. Do any of these numbers divide out of 28? Well, there is a perfect square that we can factor out, and a perfect square of 4 we can divide out. And so the reason why I picked 4 and 7 and not another combination is because 4 is the highest perfect square that we can divide out. So if I separate these into the square root of 4 and square root of 27, because, I'm sorry, 7, not 27, 28 is the same as 4 times 7. Now, if I split them up into their own roots, I can simplify that square root of 4 piece. So what happens is, this is called the most simplified version of a radical. And that's what our goal is today. After you watch this video, you should be able to simplify the radical. Now, for the second question here, it says square root of 98. Now you might need to get out your calculator and you might need to just try some numbers. So if you're not certain what numbers 98 are divisible by, start with this list. And literally what I do on my calculator is I take 98 and I look at the next highest number. Is 98 divisible by 81? No. Is 98 divisible by 64? No, not evenly. Is 98 divisible by 49? Yes. And so watch. If I take that number 49, it goes into 98 2 times. Now by my product property, I can split these up into their own roots. The square root of 49 and the square root of 2. Now what is the square root of 49? It's 7, and the 2 gets left behind. And that's it. Square root of 54, again, it doesn't matter what factors go in. What really matters is it has to be a perfect square factor, and that's kind of the goal here. Perfect square factors, so think about this list of numbers. What is the highest number in this list that 54 is divisible by? That number, the highest number, is 9. Now by my product property, I can split these up into their own roots. So the square root of 9 times the square root of 6, and the square root of 9 is 3. And this is the most simplified version of the square root of 54. Now, if you feel like you're getting it, you can go ahead and fast forward. I'm just gonna go through and do a few more examples here on the next page, and then just fast forward it until you see example 2 on the next page. So if you feel like you're getting it, go ahead and fast forward. But I'm gonna do these in case you're just feeling like I need a little bit more support. So for these questions here, try it, you try it. Using your perfect square list, what is the highest perfect square that 180 is divisible by? Pause it and try to find it. The highest perfect square that can go into 180 is 36, and it goes in 5 times. Now what you want to do is split these into their own roots. so the square root of 36, and then your square root of 5. The square root of 36 is the same as 6, and the square root of 5 part cannot be simplified because no perfect square can go into that except for 1. Now, what is the highest perfect square that 40 is divisible by? I'll give you a second. If you want to pause it now and find it, you can. The highest perfect square that can come out of 40 is a 4. Now split these up into their own individual roots and then simplify the piece that you can. So the square root of 4 is 2. 300. What is the highest perfect square that 300 is divisible by? Now you might be thinking, oh, it ends in 0, so possibly 25, but you want to find the highest perfect square, the largest perfect square, and the largest one is 100. Now split up these two radicans into their own radical signs, and now simplify the perfect square part. Square root of 100 is 10, and the radical of 3 cannot be simplified anymore. If you feel like you're getting it, you can go ahead and fast forward until I get to example 2. Here's some partner work. If you were in my class, I like to do some partner work, just like turn and talk to your neighbor and see if you're getting it. But since we're no longer in class right now, I'll go ahead and talk through these with you. The highest perfect square that 50 is divisible by is 25, and it goes in twice. Now split these up and you get the square root of 25 times the square root of 2. The square root of 25, this is your perfect square part that can be simplified down as 5, and the 2 gets left behind. Now highest perfect square that goes into 20 is 4, and it goes in 5 times. Split these up into their own radicals and then simplify your perfect square piece. Now, I didn't say this before, but you always want the whole number in front of your radical. So it goes your simplified number and then the radical behind. You would not write it like this because that's a little confusing. Is the 2 underneath the radical or not? So we say don't write it like that. Put your whole number in front. And you also don't need to put a multiply sign. It's kind of implied because they're pushed up together, kind of like 2x, you know it's 2 times x, so this is how you would write it. And square root of 108, the highest perfect square that goes in is 36, and it goes in 3 times. And if I split these up into their own radical signs, I get 6 radical 3. Okay. Now at the top of the next page, I'm going to start talking about the fractions and simplifying when you have a fraction and you have a radical that you have to deal with because you have a fraction and a radical. So for this one here, I'm going to start talking about that you can have, for rule number 2, no fractions inside of a radical. Now you can have a simplified fraction that has a radical on just the top, but you cannot have a fraction that has a radical on the bottom. So I'm going to talk about no fractions inside the radical first. Rule number 3 is that you cannot have a fraction in the bottom, but you can have a fraction in the top. So as I'm looking at this, I'm starting with rule number 2 because it's a fraction inside of the radical sign. So what I'm going to do is use the quotient property that we had on the front page and split them up into their own roots. So I'm going to take and simplify this as square root of 7 over the square root of 16. Now, can we simplify the square root of 7? Is there a perfect square that will go into that? No, 7 is prime, so the only number that would go in is 1. But the bottom we can simplify. Do you know what the square root of 16 is? It's 4. And that whole number denominator means that we have simplified this down completely. Now this one here, the square root of 18 and the number 3 on the bottom, we know there's a connection between 18 and 3. But the problem is I can't just divide 18 and 3 and say, oh, well, this is just square root of 6. It doesn't work that way because 3 is not inside of a radical. And you cannot cancel a radical with a whole number. They have to be like terms to cancel them. They need to be exactly the same term. And so it's important that you know that you cannot do 18 divided by 3 because 18 is inside of a radical, and that is not the same as 3 outside of a radical. They're not alike in terms, so you cannot cancel them because they're not alike. So what I need to do is simplify my 18 down to find the 3 piece that's in it, and here's how I'm going to do that. The square root of 18 has a perfect square that we can simplify out, and that perfect square is 9. And if I use my product property, I can simplify down the square root of 9 part by separating it from my 2. Now the square root of 9 is the number 3. And now because my 3's are alike in their term, they're not both, they're both a whole number, not one a radical and one not a radical. Now I can cancel these because they are alike in their terms, and I'm left with just a square root of 2. It's crazy to me to think that this, if I were to type it in the calculator, is the same as this decimal, but it's true. Now for this one, as I'm looking at 80 and 45, I can actually reduce my fraction. So I'm kind of thinking of this as, first I'm going to address that 80 and 45 can be reduced. Now it's a lot easier to work with smaller numbers, and so I'm going to reduce this down. Both of these numbers are divisible by 5, so I'm going to reduce my fraction before I address the radical sign. So I'm first going to just kind of look at it as a fraction. And this fraction reduced is the fraction, if I divide by 5, 16 over 9. Now, this is really easy to simplify because both of these are perfect squares. So by my quotient property, I'm going to simplify this to a square root of 16 separate from the square root of 9, and now simplify those roots. Square root of 16 is 4, and the square root of 9 is 3. Haha, nicely done. Now, if you feel like you're kind of getting it and you want to just try a few, feel free to pause the video and try these 3 and then check your answers. And then check back up when I go through multiplying. So here we go. Square root of 64, square root of 36. Do you know that these are both perfect squares? Square root of 64 is 8, and the square root of 36 is 6. Now I notice that these can be reduced. Both of these numbers are even, so if you can reduce, do so. Now both of these are outside of the radicals, so they're alike, so I can reduce the 8 and the 6 because they're not both inside the radical, or they're both outside the radical. So because they're alike in their term, we can reduce. 8 is divisible by 2, and you get 4. 6 is divisible by 2 as well, and you get 3. Now the square root of 18 and the square root of 81, this is how I simplified my roots. Now, 18 and 81, do you see that those are both in a radical symbol? Do you see that they're alike in their term? So watch this. Watch this. I'm going to make this one giant fraction and kind of do what I did here. I'm going to put them back together. 18 and 81. What do these both have in common? They both have in common, they are both divisible by, what are they both divisible by? 9. If I reduce my fraction, because they're both inside of the radicals, so because they're alike in their term, if they're both divisible by 9, I get 2 over 9. Now that I have a reduced number, the numbers are a lot smaller because I reduced, now I'm going to use my quotient property and separate my roots. So the square root of 2 and the square root of 9. Now, do you see that 9 is a perfect square? What we want to do is simplify that part. Square root of 2 cannot be reduced anymore, but the square root of 9 can, and it is the number 3. I have met my rules. I have no fractions inside of my radical anymore, and there is no radical in the denominator, so I'm good to go. It's kind of weird that you can have a radical in the numerator. You totally can, but you just cannot have it in the bottom. Okay, now 64 and 4 I reduce these. 64 is divisible by 4, isn't it? Aren't these both inside of the radical symbol? Yeah, they are. How many times does 4 go into 64? Since they're alike in terms, I can reduce. What is 64 divided by 4? It is 16. And what's the square root of 16? It's 4. Check it. Take the square root of 64, get that decimal, divide by the square root of 4, get that decimal, divide them out, you get 4. Now example 3. So when you have kind of a couple rules happening together, multiplying radicals, you can multiply radicals together. So you want to think about terms that are alike. You can multiply whole numbers with whole numbers, and you can also multiply radical numbers with radical numbers. What you can find here, though, is that it's useful to pair up radicals together, because if you can find a pair of them, then you get what's called a perfect square, because 2 times 2 is 4, and the square root of 4 is 2. And if you can find a pair, like the pair that match up, square root of 3 times square root of 3 is 9. So square root of 9, we know that's the number 3. If you can find a pair of them, what happens is the radical sign just, it disappears, because 4 times 4 is the square root of 16, which is 4. Now, 8 times 8 means I would have the square root of 8, square root of 8 times 8, which is 64, and that is 8. So if you can find a pairing, the radical sign, it doesn't technically just disappear, but that could be maybe a shortcut for you. So a pairing up can help. Now for this one here, I'm going to start just kind of using those couple properties that I had up above and start simplifying down. We actually did the square root of 12, I believe, on another paper. I think I did that on the very front. Yeah, I did. So I'm going to go back and kind of do a simplification of my square root of 12 and then address multiplying by another radical and then multiplying by the number 3. So this is what I did to start. When we talked about square root of 12 on the front page, I said that that is 4, the perfect square of 4 times 3. So that's my 12. But then I have this times square root of 3 here. Now, you can separate these, and I want to show you how I kind of view these. I view each of these pieces as individual. So what I mean by that is I have the number 3 times the square root of 4 times the square root of 3 here times this pairing, this additional square root of 3. So I broke up my square root of 12 into a 4 times 3, and the reason why I picked 4 and 3 and not 6 and 2 or 12 and 1 is because 4, the factor, is a perfect square. And now watch. 3, I'm going to leave alone for a second, but the square root of 4, this is really the number 2. And then this pairing up makes the square root of 9, which I know is the number 3. Now, I don't have any more radical signs. So because these are all alike in their term, they're all whole numbers, they're integers, I can multiply them together. 3 times 2 is 6, and 6 times 3 is 18. Now, 64 divided by 4, I'm going to show you this one maybe just slightly a different way. So if you didn't see what I did, which was putting them back together in the fraction and then reducing, is you could just look at them individually and then reduce from there. The square root of 64, that's a perfect square. It's 8. And 4 is a perfect square. The square root of 4 is 2. And what's 8 divided by 2? 4. So you can get the same answer even if you use a little bit different of a combination of the properties that I talked about on the front page, the product property or the quotient property. Now take a look at this one over here. 8 times the radical of a fraction, 3 over 16. What I did was my quotient property here, and I separated my 3 and my 16 to have a radical each for the numerator and denominator. And now what I'm going to do is simplify this square root of 16 because that's a perfect square. So this is the same thing as 8 times the square root of 3 over the number 4. Now, this is how you multiply a whole number and a fraction, regardless of whether or not it has a denominator. What you want to do is really, I look at this as like the number 8 over 1. So when you multiply fractions, you want to take the tops and multiply them together, and the bottom numbers and multiply them together. So if I multiply these together, I get 8 times the square root of 3. Now, I cannot make a 24 out of this because they're not alike in their terms. Sorry, my dog is making some noise in the background. And then 1 times 4, I can multiply those together because they are alike. They're both integers, and I get 4. Now, there's one more thing that can reduce. 8 is an integer, and 4 is an integer. And because they are alike in their term, neither of them are under a radical, I can reduce my 8 and my 4. 4 goes into 8 twice, 4 goes into 4 once. So I'm left with 2 radical 3 over 1. You don't really need to write over 1, so I'm just going to write it as 2 radical 3. Great job hanging in there so far. I'm just going to go through a few more practice problems. If you feel like you're understanding this really well and you want to go to the homework check-in and finish that next, go for it. Math, Excel, whatever your teacher has for you to do, go ahead and finish that. But if you want to see some more, feel free to hang out. I'm going to do a few more practice problems, and then at the end, totally optional, I'm going to do what I would do normally as partner practice in class, but since we're not in class currently, I figured I'd just do the whole thing on a video. Okay, again, if you're ready and you feel like you want to try the homework, go for it. If you want a little bit more help, I'm here for you. So here we go. I'm going to start with this one up here, number 19. The square root of 3 times the square root of 30 over the square root of 5. Now this is what I did to start the process. I viewed this as a fraction, kind of like the square root of 3 over 1. And when you multiply fractions, you can multiply straight across, top times the top, bottom times the bottom. Now, these are alike in terms, my square root of 3 and my square root of 30. And so what I did was I multiplied these together because 3 and 30 are both underneath the radical. I can multiply those together and I get 90. 1 is outside, 1 times anything is just itself, so then I left this as the square root of 5. Because 1 times anything is itself. Now, I notice that these are both inside of the radical. So again, they're alike in their terms. Is 90 divisible by 5? Well, yeah, because it ends in a 0. Like the rules, I feel like I learned those, gosh, maybe in like 5th grade divisibility rules, maybe even earlier than that. I'm feeling like maybe multiplication I did in 3rd grade. Anyway, I can't remember. The point is they're alike in their terms, so I can reduce this. Because 90 and 5 are both radicans, I can reduce, so reduce. How many times does 5 go into 90? Gosh, I actually legit need a calculator because my brain isn't functioning today. So here we go. 90 divided by 5. I got 18. So again, because they're both under the radical, I can do that. So I have the square root of 18. The square root I didn't address yet, so I'm getting there. Now, the square root of 18, what perfect square goes into 18? The highest perfect square. It is 9 that goes in. That's the highest perfect square. Now, by my product property, separate these radicans. What's the square root of 9? It's 3. And that's my reduced practice problem. All right, now 18 and 81. I'm going to do this a little differently here than I did on the other page. It's the same problem, but I'm going to show you kind of differently. Now, if you didn't know that these were alike and you had no idea that these were similar, and you thought just to yourself, well, gosh, I know 81 is a perfect square. Can I just start with that? Yeah, you sure can. The square root of 81 is a whole 9. So I just want to address that fact right away. And then the square root of 18, maybe you don't know what to do yet. You could leave it right here, but there is a perfect square that goes into 18. We did this problem on the other side, but the perfect square that goes into 18, the highest one is 9. Now look at this 9 from the bottom is no longer under a radical sign. So it is an integer now. It is a whole number. But this 9 here for the numerator is a radicand. It's still stuck inside of the radical sign because the square root of 18 isn't a whole 9. No, it's not 9. It's 9 times 2 still underneath of that radical sign. So I still haven't addressed the radical, but the square root of 81 is a whole perfect 9. These cannot be reduced. You cannot cancel them out because they're not alike in their term. And so we got to fix them and make them the same kind of term before we can reduce. So by my product property, I'm going to fix this up top and kind of do this process that I did over here. Do you see how what we did? Square root of 18 is 3 square roots of 2. So I'm going to rewrite the top as 3 squared of 2 over 9. Now, 3 is an integer and 9 is an integer. Because they're the same kind of term, we can reduce those terms. 3 goes into 3 once. I have 1 radical 2 on the top. Now, if you want to, you could write the 1, but it's unnecessary, so I'm going to write it in pencil so you can see that it can be erased. And then 3 goes into 9 if I reduce 3 times. That's my final answer. I love these. I don't know why, but they're kind of like a mini like challenge, like a Sudoku game to me. And I enjoy a challenge because, you know, when you conquer that challenge and then you come out the other end, there's just, I don't know, a sense of pride and like, yeah, I did it. Like, I don't know why. Math just makes me feel excited when I can get it right. So anyway, here we go. Number 21. A third times the square root of 18 times 3. Now what I want to do is put 18 and 3 together. Because they're both inside of the radical symbol, I'm going to multiply them. 18 times 3 is 54. So I'm going to rewrite this as a third of the square root of 54 because the 18 and the 3 are alike terms. They're both radicands because they're both underneath a radical sign. I can go ahead and put them back together. Now, I'm going to simplify the square root of 54. We actually did this one, if I remember, on the... Did we do this on the front page or second page? Aha. Maybe we didn't. Anyway, what is the highest perfect square that 54 is divisible by? We did do this. I was remembering right. The highest perfect square that goes in is 9, and it goes in 6 times. Okay, now, because I have found my perfect square, I'm going to separate these two by my product property. Now they're all being multiplied together. I didn't draw my multiply dot. I mean, I guess I could. What's the square root of 9? It's 3. What's a third times 3? Well, you know, these are fractions, and if we multiply straight across, 1 times 3 is 3, 3 times 1 is 3, 3 divided by 3 is 1, and that square root of 6 gets left behind. Now, I wrote the 1 in pencil just so you can know that can be erased. You don't really need it there. Now, if you feel like you're getting it, go ahead, go to that homework and move on. I'm going to go through a few more, just kind of extra practice in case you need it. If not, totally cool. I won't be offended even the slightest if you say, I'm done with this video, goodbye. All right, square root of 108. The highest perfect square that can go into this is 36, and it goes in 3 times. By my product property, I can split these up, and the square root of 36 is 6, and that's my answer. The square root of 72, the highest number, the perfect square that can go into this is also 36. It goes in twice. Now by my product property, I can split these up. The square root of 36 is 6, and the square root of 2 gets left behind. 90, the highest perfect square that goes into 90 is a 9. By my product property, split these up. The square root of 9 is 3. Now, next set here. These numbers are alike. They're inside the radical, so I'm actually going to go ahead and reduce. 98 is divisible by 2. It's 49. And we know the square root of 49. I mean, I hope you know it. It's 7. Now these, I'm not going to reduce here because 17 divided by 25, it cannot be reduced. There is no number besides 17 and 1 that goes into 17, so I'm just kind of stuck here with a fraction that cannot be reduced. So instead, I'm going to try a different approach than I tried here. I'm going to use my quotient property and split these up. Now, the numerator, the square root of 17, I just said it's prime, which means nothing can go into it. And so that's going to get left as it is, square root of 17. There's literally nothing you can do. But the square root of 25, we can fix that. That's a whole 5. Now, I've met the conditions. I simplified out my denominator's radical. We're done. You can have a radical in the numerator, just not the denominator. Okay, next. Square root of 6 over the square root of 49. I'm going to try a similar approach here because I noticed that 49 is a perfect square. Square root of 6, there's no perfect square that goes into this. That's going to get stuck as it is. But 49, that's a nice whole 7. Okay, continuing on. Square root of 108 we did up here. Do you see that problem? It's the same. So I'm going to go ahead and copy this 6 square root of 3, because I did that problem right here, over the square root of 49. We know what the square root of 49 is. Square root of 49 is 7. Then I'm done. I have met the condition that says you have no more fractions inside of the radical sign and no radicals in the denominator. Okay, the next one. 75 and 81, I don't know if they have similar factors or not. I'm not going to waste my time trying to figure that out, so I'm just going to split these up. Square root of 75. I was thinking about that problem again. Square root of 81. Now the square root of 81, hopefully you know that is the number 9. And let's talk about how we can simplify the square root of 75. What perfect square goes into 75? 25 goes in. So I'm going to split these up, square root of 25 and its own radical sign, 3 in its own radical sign. And now I'm going to simplify this square root of 25 as 5. Now, this 3 is it's a radicand. It's inside of the root. It cannot simplify with an integer. They're not alike, so don't be tempted to reduce here. You can't, because they're not alike terms, and you can only cancel and multiply like terms. And so just make sure that you simplify correctly. All right, one more. 5 times 20. That's 100. What's the square root of 100? It's 10. I hope you're having an awesome day. I hope you're safe. I hope you're well. I hope you're healthy. And check me out in the next video.